So that's the field. And we said the field is uniform. So what is my perturbation Hamiltonian now? It's precisely the same as we had in the static case 2 weeks ago. This is still electric fields going to enter via the scalar potential. So we get a perturbation Hamiltonian, and I think in that chapter it's called V. V of t is then going to be minus the dipole moment operator times this now time-dependent field. Okay, so we have Hamiltonian for our molecule in the presence of this electromagnetic radiation. The Hamiltonian is then the field-free Hamiltonian without the perturbations, and this perturbation. And to be sort of consistent with the notation I used previously, I might as well call that H1 of t. Well, I think in the in our textbooks it's called V of t. V of t, and I might put a hat on it. Okay, that's our Hamiltonian, and this Hamiltonian now is time dependent, which means we have to go back to the real original Schrödinger equation, which is the time dependent Schrödinger equation. That's our equation now which we have to solve. So we're going to look at this expression. Let's assume we get a ground state. Hamiltonian and right, so back to the time-dependent Schrödinger equation. And if you want to go on, we have to solve this equation in some way or another. Now, if we just take the unperturbed Hamiltonian without a field, insert that here, then we don't have a time dependence in the Hamiltonian any longer, and then we can separate the variables, like always separation of variables, and we can derive at the time independent Schrödinger equation, the one we looked at all the time, and we get an expression for the time dependence, a separate equation for the time dependence of the wave function. And then we can also solve that. And that gives a phase factor, a time-dependent phase factor for the wave function, which we so far never have considered. But even in the case if the Hamiltonian has no time dependence, the wave function, the real solution to the Schrödinger equation, the time-dependent Schrödinger equation, is still time-dependent. It's a very simple time dependence because it's just a phase factor. So our zeroth time-dependent zeroth order wave function is going to be a product of the solution to the time-independent Schrödinger equation times the time dependence, the solution to the equation which expresses the time dependence. And how do I want to write that? There we go. So this zeroth order, now like this is the solution to the time-independent Schrödinger equation. So that's the solution to this equation. That's a time-independent Schrödinger equation with the unperturbed Hamiltonian. So that solution, that times a phase factor, which is an exponential. And in most cases, you might have seen it written like this: I H bar. But here I want to actually use it not with the energy already, but with the 0th order Hamiltonian, which is the same because that is an eigenfunction to H0. So if I let H0 act on that state, I just get the energy. This is an exponential operator, very much like we had exponential operators in the case of couple cluster theory. And the way this works is you expand it in the series expansion and having then powers of the operator acting on that. But since it's an eigenfunction, it gives me the energy, so I can write it like this.